Hello and welcome to part 4 of AQA Chemistry, Higher Tier 2018. So I guess I'll straight with the questions. This is part 4. The number of moles of each gas produced at the electrodes is the same. No gas escapes in the apparatus. Suggest one reason for the difference in volume of each gas collected. So let's have a look, let's remind ourselves, because it was a little while back here. Okay, so we've got test tubes collecting hydrogen and chlorine. So more hydrogen was collected than chlorine until it's kind of pushed the sodium chloride solution. So that salt dissolved in water, more hydrogen's displaced it. So that gives us a clue of how to answer that question. So, not quite on to calculate yet. So suggest one reason for the difference in volume of each gas collected. So more hydrogen was collected. Let's start with that. So more hydrogen was collected as chlorine dissolves in water. You've got a swimming pool, it's got chlorine in it to kill bacteria, because chlorine dissolves in water. Hydrogen doesn't dissolve in water. Okay, you get bubbles of hydrogen, it doesn't dissolve. Okay, you get some bubbles of chlorine, but it quickly dissolves usually. The bubbles are smaller. So it says calculate the amount of moles, calculate the amount in moles, of chlorine collected after 20 minutes. Use figure 8. So you can look at the graph. The volume of 1 mole of any gas at room temperature and pressure is 24 decimeters cubed. Give your answer in standard form. So let's have a look. 20 minutes. Okay, so 20 minutes and chlorine. So that was, each one is 0.2, so 6.246, 6.6. Let's write that down to start with. So, let's check the unit. Didn't check the unit. That's important too. Centimeters cubed. So you need a conversion. Okay, 6.6. 6.6 centimeters cubed of chlorine gas produced. Okay, and let's have a look. So how many moles? So we need to work out how many decimeters this is. So decimeters is a cube. So there's a volume of sides 10 by 10 by 10. Okay, 10, 10, 10 centimeters, I should have said. Okay, so 10 times 10 is 100, times 10 is 1,000. So there's 1,000 centimeters cubed in 1 dm cubed. Okay, so we need to do 6.6 divided by 1,000. Okay, to get 0.0, it's going to be a small number, that's what we need standard form, isn't it? 0.06, look at my calculator there. 0.0, because yeah, you definitely need to do a calculator. The well, you could do it with that one, but I would just recommend you use one because you can use one in an exam. So that's in dm cubed. We're pretty much nearly all there. Now we need moles, and we are told that 1 mole occupies 24 dm cubed. So we just need to do 0.0066 dm cubed divided by 24. Okay, so that's going to give us, yeah, you can tell a small number, 2.75 times 10 to the minus 4, and it's moles, and they've given us that. So we only need to write that number in. So it's all about conversions, that one. Okay, it's it looks like it's going to be a lot more complicated than that, but it's getting used to the conversions there about how many centimetre cubed decimeter, and we're told the volume of gas. Okay. Okay, so let's go on to the next one. So the question is about group 7 elements. So they're also called the halogens. Chlorine is more reactive than iodine. Name products formed when chlorine solution reacts with potassium iodide solution. So obviously that's an important statement. So chlorine reacts with potassium iodide. So if chlorine is more reactive, the potassium iodide, the iodine would get kicked out of solution. Okay, so it would form potassium chloride and iodine. The iodine's getting displaced. That's why we've been told that. Okay. Explain why chlorine is more reactive than iodine. Okay, so why chlorine is more reactive than iodine? So it's group 7, so it's a bit different to group 1. Okay, so group 7, let's explain a little bit first. So group 7 elements, they want an additional electron. Want 1 electron to fill outer shells. Okay. Chlorine, the chlorine's outer electrons are closer to the nucleus than iodines. So chlorine can gain electrons more easily as the nuclear attraction is stronger. Remember, the nucleus is positive. Okay, so it's going to attract those electrons. Okay, good. Oh, we've got some, let's go up a little bit. So bromine, so we've got another halogen there. So bromine reacts with methane in sunlight. Okay, that's an interesting reaction. So figure 9 shows the displayed formula for the reaction of bromine with methane. Okay, it's an interesting reaction. So we've got hydrocarbon reacting with a halogen. So you've got methane reacting with bromine, Br2, remember? Okay, Br2 goes to it's a bromine, there's a haloalkane, okay, and HBr. So table 3 shows the bond energies and the overall energy change in the reaction. Okay, so we've got bond energies is the bright bond here, like the carbon-hydrogen bond, 412, bromine-bromine, 193, CBr, this one, oh, unknown, I'm going to work that out, HBr, 366. Overall change, minus 51. Okay, so it's losing that energy. So let's look at what we need to do. Calculate the bond energy. Ooh, so that's 7.4. Oh, sorry, I missed the question. Sorry, go back. Sorry. Chlorine, so let's go back. We're going to leave that question. We'll come back to it. Sorry. Chlorine reacts with hydrogen to form hydrogen chloride. Explain why hydrogen chloride is a gas at room temperature. Answer in terms of structure and bonding. I thought I missed a question out there. So yeah, this one. Chlorine reacts with hydrogen. So hydrogen chloride. So it's HCl. So hydrogen chloride, HCl, is made of simple small molecules. It's not a big structure. When you have hydrochloric acid, it's hydrogen chloride dissolved in water. So hydrogen chloride, so I've got HCl, it's hydrogen chloride, has weak intermolecular forces. Okay, which do not need much energy to overcome. Okay, so that's what's gas, because its boiling point is very low. Okay, it's even lower than water at room temperature. Let's go back to this then. Okay, so let's go back to that. We've got the bond energy. We need to find the missing value. We talked about it. The bond energy change. Use figure 9, and so we've got so bonds broken and bonds formed. Okay, so let's go on the left-hand side. Which bonds are broken there? Let's write that down. So bonds broken. Okay, so we've got CH bond is broken. So are they all broken? We've got 412. 412. Calculate the bonding. Okay, so you've got 4 times 412 to break that molecule apart. Put that in the bracket, plus 193 equals 1841. Bonds formed to reform that molecule and that one. So let's do it on a separate line. Bonds, it's like a maths question really. Bonds formed equals 3 times 412, because there's only 3 carbons, plus that HXPR, plus X. Okay. So that equals, yeah, it's a maths problem, 1602 plus X. So we've got minus 51, the overall one, equals 1841 minus 1602 plus X. Okay, so if we work that out, we have 290 kilojoules per mole. Okay, the missing value of X is 290. Okay. So let's go on to the next one here. Okay, titanium is a transition metal. Titanium is extracted from lithium, sorry, let's go back. Titanium is extracted from titanium dioxide in 2 stages, a 2-stage industrial process. Stage 1, titanium oxide plus carbon plus chlorine goes to titanium chloride plus 2 carbon monoxide. That's stage 1. Stage 2, titanium chloride plus sodium goes to titanium metal plus 4 NaCl. So just one hazard associated with stage 1. So one hazard associated with stage 1 is chlorine gas is toxic. Okay. Also carbon monoxide. So I'm going to put both here, but we only need one. So chlorine is actually actively dangerous, actually toxic, because carbon monoxide suffocates you. It's toxic in a different way. Okay, chlorine is toxic. It's very, very dangerous, chlorine on its own. Okay, so always be careful when you're working with chlorine. So I'm just going to stop the video there, and I'll continue in part 5. So thank you for listening, and I'll continue in part 5. Thank you. Goodbye.